We are going to talk some more about the trig substitutions today. We do have homework due today. Check it out, and we'll have our quiz on Friday as usual based on the content from the homework. But I want to talk some more about trig substitutions, just do a few more examples. So if you recall from last time, the trick that we talked about doing, or the substitution we talked about last time was this one. If you see square root of some constant minus x squared, the substitution, and this you just have to remember this strategy. If you see that square root a squared minus x squared, then you do the substitution x equals a sine theta. And of course that makes dx equal a cosine theta, d theta. And then you rewrite the inside of the square root there as a squared minus a squared sine squared theta becomes a squared cosine theta. This looks kind of complicated when I write it in this way, but really in the individual examples it works out just fine. It means the thing inside the square root will become a squared cosine squared theta, and then you take the square root and it just becomes a cosine theta. All right, this was the trick from last time. We did some examples. I want to talk today about a very similar trick, which everything basically goes the same way. So this time I want to do an example where...
Professor, is that a squared cosine squared theta? Or is that just a squared?
Yes, thank you. It should be cosine squared right there. Yeah. The reason you do this is then, the way that this will always work out in these examples, a squared minus x squared becomes the square root of a squared cosine squared theta, which is equal to a cosine theta. That's the point of this substitution, is it allows you to get rid of the square root sign, which is usually like the principal obstacle to doing the integral. All right. Yeah, sorry about that typo. So this is what we did last time. A very similar trick works. Similarly, if you see square root a squared plus x squared, so that one that I just said works when it's a minus in the square root. What if it's a plus in the square root? In this case, there's a similar trick you can do. So in this case, you do, this one is, very slightly weirder. It turns out using the tangent in this case works. X equals tan theta. And then dx will be the derivative of tan. Anybody remember this? Derivative of tangent is? Secant squared theta. Yeah. D theta, of course. And there is also a rule about, so analogous to this one here. This, remember, comes from 1 minus sine squared equals cosine squared. There's a similar rule about tan and secant, and the rule about tan and secant is 1 plus tan squared theta equals secant squared theta. And so when you do this substitution here, I will say you also use a squared plus a squared tan squared theta equals secant squared theta. And so that means that the square root of a squared plus x squared will become square root of, sorry, I left out a, square root of a squared secant squared theta, which will just be a secant theta. All right. So using tangent and secant will allow you to get rid of a square root sign that has a plus in it. And if it has a minus in it, you use sine and cosine, right? But otherwise, these two tricks, they work in the same way. So let's try one like that, using the tangent, using the tangent and the secants. So you can put this in a box somewhere, I guess. These are like the two different trig substitutions that you might want to use. All right. If you look in the book, actually, they do another one in the book, which I don't want to get into, but it's for handling another slightly different situation. satisfied. I'm satisfied with just doing these two. Okay, let's try an example of this one using the tangent. They really play out the same way. You just have to remember which is which, or which to use when. So let's try this. 1 over square root, 1 over x squared times square root 25 plus x squared, like that. All right. So since I see the square root of, something squared plus x squared, this should cause you to recall this second type of substitution that I just said, right? Now, there's an extra x squared out there, which maybe concerns you. I say, don't worry about it. Everything's going to be fine. Let's do it then. So I'm going to do x equal tan theta, which means dx is going to be secant squared theta. That's the OBS screen, which is a screen recording software I'm using. Sometimes it happens. It seems to happen less when I have less things open. I was just listening to my iTunes, so I'm quitting my other apps. Sorry about that. All right, we'll see if it happens again. Not a big deal, I guess. Okay, so this is the substitution. X equal. Sorry, I forgot that. I left out the A. I left out the. Did I leave out the A everywhere? I wrote. Sorry about this. I wrote it in here. The substitution needs to include the A. A tan x, then dx is a secant squared x. Otherwise, everything that I wrote is accurate. Sorry about that. Can you insert the a's there? The a has to be part of the substitution. So what you see inside the integral has an a squared plus x squared. You have to decide what the a is. So in this example here that I'm doing, what's the a going to be? It is 5, yeah, because this is 25, which is 5 squared plus x squared. So my substitution needs to say x equals 5 tan theta, which means dx is 5 secant squared theta d theta. Sorry about that. Okay, anyway, let's plug them in. So right here, we plug everything in. Where I see x squared, I guess, becomes 25 tan squared theta. And then the square root, 25 plus another x squared, 25 tan squared theta. And then dx on the outside will become 5 secant squared theta d theta. All right, I just plugged in for my substitution. Remember, when you do x squared, you've got to square the 5 and also square the tan theta. So it becomes 25 tan squared theta. Alrighty. And now we're going to try to simplify everything. So first of all, the square root part will simplify according to this, what I wrote at the very end here. So inside the square root turns into, I'll just leave this like it is for now, 25 tan squared theta. Inside the square root turns into 25 secant squared theta. 5 secant theta over here. Because, no, it just, I'm using this formula for the tangent. So this is a true fact about the tangent, which is related to the fact that sine squared plus cosine squared equals 1 if you rearrange everything. So when I see 25 plus 25 tan squared theta, that's the same as 25 secant squared theta. And this is the real sort of heart and soul of the substitution, because now I can do the square root, right? The square root can happen here, and what remains is 25 tan squared theta, and then the square root of that becomes just 5 secant theta, right? You square root the 25, you also square root the secant square. and then times over here 5 secant theta, d theta. Secant, this over, sorry, I'm not doing so well today. This over here should be secant squared. I got it right here. I forgot about the square as I went down. So these are secant squareds. Secant squareds.
So are you multiplying the whole equation by 5 secant squared by that third step? Or is that 5 secant squared just on the top?
This here?
Yeah.
Oh yeah, you can put it in the top of the fraction, or you can. I mean, I'm going to cancel one of the secants, right? I have one secant in the denominator here, so that can cancel with this secant over there in the numerator a little bit, and the 5s can cancel too. So this is going to be 5 and 5 cancel, right? The 25 in the denominator, I'm trying to clean up the inside of the integral here so that we can do the integral. The 5s cancel. The 25 in the denominator can just pull all the way out of the integral. So I'm going to put 1 over 25 in here. And then what remains is a secant and a tan squared on the bottom, right? Because one of the secants canceled. I had a secant squared in a numerator and a secant in the denominator. So one of them's canceled, and then I still have tan squared in the bottom. All right. And now, just because I find it easier to think about things when they're all sines and cosines, can we... let's just rewrite this using sines and cosines. You know, tan is sine over cosine, and secant is 1 over cosine. So what this is, I find it helpful to express everything just in terms of sines and cosines, because some stuff is going to cancel out here. The secant in the numerator is the same as a 1 over cosine, and then the tan squared in the bottom is the same as cosine squared over sine squared. Since tan was in the denominator, I wrote it as a reciprocal instead. Tan is sine over cosine, so I wrote cosine over sine. And then here, we can cancel a little bit more, right? I have a cosine on the top and a cosine on the bottom. So this is really cosine theta over sine squared theta, d theta. And that is as simplified as the inside is going to get, I think. All right. Any thoughts so far? We're not quite done, but we're getting there. Anybody got an idea? How can we actually do this integral? Cosine theta over sine squared theta? Are you lost about how we got here or where we're going next? There's a lot of just simplifying the formula a lot. Yep. How can we handle an integral like this? No. L'Hopital is only about doing the limits of something. I'm going to write this a little more suggestive content. Yeah, you can do a u substitution here, where u is sine theta, and then du will be cosine theta d theta, and it'll all work out great. So I'm going to do u equals sine theta, du is cosine theta d theta, right? So what does it look like after you plug everything in terms of change everything into u's? What does it look like after that? Yeah, u to the minus 2 power du. I like that. Right? The u is sine theta, which is in the bottom with a power of 2. So we can write it as u to the minus 2. And then the rest of it, cosine theta d theta, is the du. Excellent. So now we can finally do this integral. We get 1 over 25, and then I guess minus u to the minus 1, right? So this is negative, if you want, you can write it this way. Negative 1 over 25u. Although I don't care how you write that. Okay, now we're basically done at this point, although you got to go back and express everything in terms of the original variable, which is x, right? Now, first of all, I can plug the theta back in for u. So this is minus 1 over 25 sine theta, right? Because u equals sine theta. But now I want to go even further back and say what it is in terms of x. So in terms of x, you have to remember the original substitution was x equal tan theta. So how can I, 5 tan theta, right? Forgot the 5 again. X equals 5 tan theta. And we did this on a couple of examples last time. How do we solve that for theta in terms of x? That's what I want to do. I would divide by 5 first. So this is x over 5 equals tan theta. And then use the inverse tangent. Theta is inverse tan of x over 5. So this is minus 1 over 25 sine of inverse tan of x over 5. I suppose I should have put the plus c. You could just stick it on the end, but really, technically, the plus c should be introduced at this step. One step earlier. This step here, because that's the step at which I actually did the antiderivative. So, but I don't care if you just save the plus c to the end. That's fine too. All right. One more step. We've been doing this one example for 15 minutes. These are a little taxing. One last step is to simplify the trig inside of the inverse trig, or the inverse trig inside of the trig. All right. Can we simplify sine of inverse tan of x over 5? Remember how to do this is you draw a little triangle whose tangent equals x over 5, and then you find the sine of that. So my triangle, the tan is supposed to equal x over 5. That means the opposite over the adjacent is x over 5. So that's this and this. Opposite over adjacent is what the tan is. So this is the angle, which is the inverse tangent of x over 5. And now I want to know what is the sine of that. It's the opposite over the hypotenuse. The hypotenuse in this case will be square root 25 plus x squared. That's the Pythagorean theorem. And then the sine of that, so the sine of this is x over that square root. This is the opposite over the hypotenuse. From that angle, the opposite is x, and the hypotenuse is square root 25 plus x squared. All right, so this goes right here. So my final answer is, you ready for this? This is really the end. Negative 1 over 25 times this thing, x over square root 25 plus x squared. Because that's the sine of the inverse tangent of x over 5. Yep. And if you don't like, fraction inside denominator, you can flip this around. I don't care about this, but you could say it's minus square root 25 plus x squared over 25x. That's what it is. All right. Yeah, it's pretty. It's quite a process. I think each individual step is not so hard, but you can easily get lost in the details because there's a lot of little steps in there. I want you guys to try one similar to that one we just did. I think maybe a little easier. I don't know. Unless are there specific questions about this one? I think the way to learn this, like most things in this class, is just to try and do one yourself. You should be able to kind of copy the steps that we did in this one on this next one. So I would like you to do integral x times 4 minus x squared dx. And I would like you to use the trig substitution. Now, this one, actually, the trig substitution is not necessary. You can do a much easier u substitution to get the answer. So maybe while you guys are doing it the hard way, I will do it the easier way, and we'll see if you get the same answer as I do. All right? Is that demoralizing to make you do it the hard way while I do it the easy way? This is possible to do in an easier way. If you instead put an x squared here, then it becomes only possible using the trig substitution, but then it's a lot harder. It's easier for you guys to do it just the x there. All right, so. Yeah, so this one, your first realization is there's a minus in there, so you shouldn't use the tangent like I just did. You should instead use the sine. But the details of the problem otherwise are, you do all the same types of stuff. So the way I'm doing it on the screen is not what you should be doing. I'm doing it the easy way. If you actually get an answer, it should be the same as what I have here. Any questions from the folks at home? Nope. All right. If this seems hard to you, then it is. I'm going to start writing down my You do a U substitution?
Oh, you make that.
Yeah, similar to the example we just did. Seems like people are doing pretty well. I'll give you a few more minutes, and I'm proceeding with my solution here. The inverse sign? Yeah. So it'll say x over 2 equals sine theta, and to solve for the theta, you do the inverse sign on both sides. Yeah. Almost there, yeah. That's right, yeah. Sure. I mean, you're going to do the homework, so that's something. And on the quiz, the quiz is only meant to be like 10 minutes long, so I'm not going to give you one. Be simpler than, like, even this will take you that long to do just one example. All right, can we talk about this? I see most people are either done, well, everybody's either done or almost done. So let's just, everybody got started off, I hope, in the right spot. This is the substitution you should make. Oh, actually, first of all, can we look at the easier way to do it? So in this particular example, you can do a very standard U substitution because the inside of the square root is 4 minus x squared, and then I can make that the u. Then the du becomes negative 2x dx. I have the x out here together with the dx, which will allow the substitution to work. So you get square root u times negative a half du, and then you do this business, and it eventually ends up like this. 3/2 power with the negative 1/3 in the front. So this is what we're going to check our answer against. That's the easier way to do this. Now, on a test or something, I would, like, part of what the skills you're going to develop are being able to look at the integral and decide which of these techniques you're supposed to use or which would be the best. You know, by now we have several methods. There's the integration by parts, there's a simple u substitution, or one of these fancy trig substitutions. And so if this problem were on the test, I would hope you would realize that you can do a simple u substitution to do it. Although I might tell you, or I might make you do the trig substitution just if I want you to, I want to see that you know how to do it. Anyway, in this case, the appropriate trig substitution is this. I forgot to write d theta here. As I was walking around, I saw everybody pretty much did the, you know, everything correctly eventually. This 2 sine theta came from the x at the beginning, and then we had the square root part, which looks like this when you plug in, and then we have the dx part, which looks like this when you plug in. And doing a bunch of simplifications without messing it up anywhere, you should end up with something like this. 8 factors out, and then I have sine squared, and then cosine sine of theta, and then cosine of theta squared. Then I do this u substitution, and I end up with something like this, just u squared times negative du. Do the antiderivative, and then plug in the theta again. So this is as far as I got. Are there any questions about that so far? I think everybody in the room did all right with that. Any questions from the folks back home? I hope you're following along. I know this is tricky stuff. Anyway, just to finish it off, I want to put the x value, the x variable back in. Now, as I've been doing this earlier, you know, come on now. It'll be back soon. I quit my other apps. I don't know why. Remember, sine theta equals x over 2. It's actually, in a problem like this, it's not strictly necessary to solve for theta here using the inverse sign. You can actually just, right from here, draw your triangle, right? Since it says sine of theta equals x over 2, that means that theta is this angle, and the sides of the triangle are x over 2, right? This is the opposite over the hypotenuse, is x over 2. And then what I want over here is to find the cosine of theta, and that's, you know, we can do that, right? The other side here should be 4 minus x squared, and then the cosine of theta should be the adjacent, this is the theta, the adjacent over the hypotenuse. So this is going to be minus 8/3 square root 4 minus x squared over 2. All of that is cubed plus c. And this is your final answer. Now, just for the sake of seeing if you get the same thing that I got, you can simplify. Really, there's not much to say here in terms of simplifying, although I can cube the thing inside the parentheses. This now would become this to the 3/2 because it's a square root but being cubed. That's what 3/2 means. And then on the bottom, it's an 8. And the 8's cancel, and you get this, which is what I said at the beginning. There you go. What do you think? Any questions about this? You know, as I walked around, everybody got this eventually. Although I think there is a lot of opportunity to mess it up in there. A lot of little ins and outs, a lot of what have yous, as they say. All right. Great. That is the trigonometric substitution. And this is all I want to do with those. So, like I said, there is another type of trig substitution that they talk about in the book, and I figured this is enough for me. All right? I hope you are of the same mind. Okay, we got 10 more minutes. I think we can do a little introduction to the next section. The next section is yet another trick for doing some other kind of weird integrals that you couldn't do before. It's called, so the next section is called integration by, the trick is called partial fractions. Partial fractions. I kind of like the partial fractions. Would you let me be honest here? I don't really like the trig substitution. I think it's cool that the trig substitution actually works, because to me it seems like such a weird idea, but it does actually work. There's some satisfaction, in my opinion, to making the trig substitution actually work, although it's I find myself more satisfied doing the partial fractions. I like the partial fractions a little bit better than that. It is based on, I know we only got 10 minutes here. Before I tell you about the partial fractions, can I just say we're going to use this formula all the time when we do partial fractions. This one, I mean, everybody knows this formula. There is a slight variation which is actually more useful, and it's this. If instead of x on the bottom, you have some other sort of linear polynomial on the bottom. So the question in our minds is, you know, what difference does it make if you have a constant multiple in front of the x and also a constant thing added onto the x? And I'm here to tell you, this is what difference it makes. You get this. 1 over a, ax plus b. Sorry, 1 over a, the natural log ax plus b plus c. This is a true formula. How would you become convinced that this formula is true? Well, on the left side, you can do a u substitution. U equals ax plus b. And then if you work through the substitution, you'll get the thing on the right. Or another way that I could demonstrate this to you, I'll write this as if it were a little proof. What's the derivative of the right-hand side? Derivative of 1 over a ln absolute value ax plus b. What you get is the 1 over a is a coefficient, so that will stay as a coefficient. And then what's the derivative of the natural log of all that? Well, it's 1 over the inside. And then the chain rule says I have to multiply by the derivative of the inside, which is a. And that 1 over a in the front will cancel the a at the end, and what you end up with is just 1 over ax plus b, which is what I wanted, right? I took the derivative of the thing on the right, and I got the thing on the left as the answer, which means the derivative, that means the antiderivative of the left side equals the right side, okay? So, I hope you are now convinced that this formula is true. Like I said, we're going to use this all the time when we do the integration by partial fractions trick. Here's a simple example of the partial fractions trick. It's a little magical. You use the partial fractions when you have a, what they call a rational function. This is called a rational function. That means a fraction with polynomials on the top and the bottom. A fraction of polynomials. I wrote polynomials. That's supposed to say polynomials. All right, that's called a rational function. And the way to integrate a rational function, sometimes you get lucky and you can do a u substitution using the denominator as the u and then the du as the numerator. But in this case, the numerator is not equal to the derivative of the denominator, and so that trick is not going to work. Instead, we use the partial fractions trick. And here's what it looks like. It turns out that this 1 over x squared minus 3x plus 4, it equals 1/5 over x minus 4 plus negative 1/5 over x plus 1. This step is called the partial fractions. Now, since I told you this is true, this is not hard to verify. What you would have to do to verify this, what I just told you, is make a common denominator on the right-hand side and add those two fractions together. And you will see that you do indeed get the thing on the left-hand side, all right? This is called, this formula here, this is called a partial fractions decomposition. And the whole sort of meat of the partial fractions trick is, how did I figure that out? And this is something that I don't think we have time to get to today, but next time, we'll spend the bulk of the time talking about how did I get those denominators in the first place, and how did I get the numerators of 1/5 and -1/5. But this is the heart and soul of the partial fractions trick. You rewrite. Yes.
Is that essentially factoring that?
Yeah. The two denominators you will notice are the factors of what you started with. The more interesting question is, how do you figure out the numerators? They seem to be sort of pulled out of nowhere. Now, if you do actually add these together with the common denominator, you will see that these are the proper numerators to use. But if you didn't know them already, it's not so obvious how you'd figure them out. Anyway, that's the basis of the partial fractions trick. Just for now, since we don't have time to get into that, can we show how do you use this to do the integral? Well, that means that the integral of the original thing is equal to the integral of, written this way, right, partial fractions. And now we can do those integrals. Each of them looks like a natural log of something, right? Remember that thing that I told you a few moments ago? This formula, right? Oh, I moved my screen. We're going to use this on each of those two things which you saw inside the integral, which were added together. So right here, I have two terms. Each of them becomes a natural log of something or other. And those numerators, they just end up being like coefficients. They're just constant multiples. So this becomes 1/5 natural log, absolute value, x minus 4. That's what happens to the first one. Plus, or I guess minus, 1/5 natural log, absolute value, x plus 1. And this is my final answer, right? So what I used there was this thing, integral ax plus b is equal to 1/8 natural log absolute value ax plus b. Now in this example, the a's were both 1, so we didn't have to worry about the a's. The b's were the 4 and the 1. They don't really matter. They just, they don't do much. They do appear in the answer, but you don't have to worry about them. All right, this is the partial fractions trick. You start with some kind of big rational function. It involves factoring the denominator and somehow figuring out what these numerators ought to be. And then you can just do the integral in terms of some natural logs. All right? So I will leave it until Friday, the tantalizing cliffhanger. How do you get the numerators? That's really what the partial fractions trick is all about. All right? Have a good one. See you on Friday. Goodbye to the folks at home.